Okay, we have completed the material balance for the ammonia oxidation reaction to nitric acid, and now we do the energy balance. Now the energy balance reduces to, in this type of situation, as Q, the heat, is equal to the change in enthalpy. All the other terms such as kinetic energy, potential energy, shaft work are not present here. Now the change in enthalpy is equal to the change in enthalpy due to reaction times the extent of reaction. So that's the extent times delta H R. Now we're going to use the heat of reaction at standard conditions, then plus the enthalpy of the outlet materials, Ni, 8Hi, then minus the enthalpy of the inlet materials, Ni, Hi. And these enthalpies will have to have the same reference state as the heat of reaction, which in this case is 25 degrees C and gases. Now with these type of reactions, the most systematic and convenient way to handle all these different enthalpies is to use an enthalpy table. So first of all, we'll state explicitly what the reference state is. And that will be, because our heat of reaction is at this state, 25 degrees C and gases. So our table will have these headings: the species, the number of moles in, the enthalpy, specific enthalpy of each of those chemicals as they are coming into the reactor. I like to have another column in here which is the total enthalpy. Remove that hat. The total enthalpy, which is the number of moles times the specific enthalpy, in, and then also the same columns for the outlet material. Okay, so we have chemicals A, B, C, D as a liquid, and D as a gas. Now all the other chemicals are gases, so I suppose I could write that next to them also. All right. Now the N in, number of moles in and out, were already calculated. Those are 40 for A, 40 for B, those were specified, and 20 moles of liquid D, no C, no nitric oxide, and no water gas are coming into the reactor. At coming out, the material balance yielded 20 moles of A. B had 15 moles. C had 20 moles. D had 50 moles. These are all gases, so I should put the D not there, but in the gas row, 50. So there was no liquid coming out. Now to calculate the enthalpies, now we have to take our gases and determine the enthalpy of raising the temperature from 25 degrees to the inlet temperature, which was 75 degrees. So we calculate the enthalpy of the gases A and B coming in as the integral from 25 degrees, that's the reference condition, to 75 degrees, Cp dt. Now for the liquid water coming in, it's a little different because we're stating that the gas at 25 degrees C is the reference condition. So we need to go from that condition to a liquid at 75 degrees. So the first thing we need to do is take that liquid up to the boiling point so we can condense it, because that's where we know the heat of vaporization, or the opposite of the heat of condensation. So the first step will be to go from 25 degrees to 100 degrees Cp dt, and that's the liquid, then minus the heat of vaporization because we're actually condensing it, and then plus the integral from 100 down to 75, which is the actual temperature of the inlet, Cp dt, and that's for the gas. On the product side, they're all gases at 300 degrees C, and so all of these will have the enthalpy being from 25, the reference condition, to 300 degrees, and that will be of the heat capacity integrated between those temperatures dt. Now, go to the spreadsheet, which is called Energy Balance with Reaction Tutorial, and look at the first tab, which is given DHR, which means the heat of reaction. At the top of the spreadsheet, it'll say Problem 9, nitric oxide production using the given heat of reaction. And you can see all these enthalpies calculated in the enthalpy table. So here is the enthalpy table filled out for this particular reference state, which was 25 degrees C and gases, using the given heat of reaction. So now what we'll do is sum up these total enthalpy streams. That's minus 667 here, and these are all kilojoules per mole, kilojoules. And this column, the outlet column, is a positive 995. So the grand finale then, Q, is equal to the extended reaction, which was 5, times the heat of reaction, which was given as minus 904.7, plus the enthalpy of the outlet streams, which was 995, minus the enthalpy of the inlet stream, which is a positive, which is a negative, so it becomes a positive, plus 667. And the grand finale then for Q is minus 2861. So 2,861 kilojoules must be removed from this reactor. Now, other tutorials will show you how to do this calculation with other reference states.